for copper, we were expecting 4s2, 3d, how many? 9, 3d 9. And so when I look at the D subshell, this is what I envision. I envision like a 2-layer cake again. The bottom layer is filled. However, the top layer just has one piece taken out of it. Just one. And so we can complete this by just adding one more. And so what do we do? Take one from the 4s and promote it to the 3d. And so we expected 4s2, 3d 9, but that's not what's observed. What's observed is this. It's going to be 4s1, 3d 10 because of the stability of the filled D subshell. Do you recall the shape of the D orbitals? S orbitals are spheres. P orbitals look like what? Yeah, like that figure 8 type thing. D orbitals look like what? Clover leaves, yeah. 4-leaf clovers. It turns out when you take, all 5 d orbitals and put them together, you take then it looks like a sphere, when you take all and so it's not like a cake like this. It's a spherical cake, and that's what happens. The same thing with the P. When you take all the P's and then just visualize it, it kind of looks like a sphere. It has what we call spherical symmetry, just like the S. The S are definitely spherical symmetry, but if the P's are all filled, that has spherical symmetry as well. And if the D's are all filled, that has spherical symmetry. And half filled, if you half fill it like this, all the way across, that has spherical symmetry too. So the significance of this is that you got that spherical symmetry with the half filled and the filled orbital levels and subshells. And so this is what gives us this exception. Copper is a 4s1, 3d 10 because we're just one slice away, and it's okay to promote one. If we're 2 slices, like nickel's 2 slices away, 2 electrons away, but we aren't going to sacrifice the 4s completely. Here. And then zinc goes back to normal. Here, 4s 3d 10. Zinc is. Okay, now we are going to identify things. We're going to label some of these electrons. We have valence versus core electrons. The core electrons, these are inner shell electrons. And valence is the outermost shell of electrons. Now this gets tricky because some of these shells, like the 4th shell in particular, is a little bit tricky. The 4th shell, but the other shells are pretty easy. And so outermost, we'll have to define this as the highest n orbitals. Valence versus. No, just n dash. And hyphen orbitals. The highest n orbitals. I'll tell you what I mean by that in a minute. Like right now, I can tell you what it means here. When I look at the shells, the inner shells would be the first shell's inner, the second shell's inner, the third shell's inner. The outer shell here looks like to be the 4th shell, right? The 4th shell is the outermost shell. It has electrons in. The 5th shell is totally empty. And so it looks like the outermost shell on this is the fourth shell. But here, the core electrons are a bit tricky here. And so when we do valence and core, we rewrite the electron configuration sometimes to help us. Sometimes electron configuration is rewritten in numerical order. So for example, we know that copper is argon, if I use the abbreviation here, 4s1,3d10. But what I do here is I rewrite this to argon 3d10 4s1. Now 3d10, that's kind of stable. We don't want to mess with it. It's filled. Although it's not a completely filled shell, it's this filled subshell. And so this is tricky because we consider up to here the core. Even though this is the argon core, it's the argon core plus the 3d10. And the whole thing will be labeled core electrons. Core electrons. And so the valence electrons will be the 4s1. This will be valence. Now if you're ever confused about this, remember the highest n. What is the highest n? 4. And so the valence electrons will all have n equals 4. 3 is not. 3 is inner. And so what this is why do we care? Why we care is this. If you're an oxidizing agent, what do you want? What do you want to take? If you're an oxidizer, you want to take electrons. If you're an oxidizer, you want to take electrons, you're going to take the electrons closest to the center of the atom or furthest away from the center of the atom? The furthest away. Now, which electrons are the furthest away? The electrons in the highest n. Because each n, let's say n equals 1, like this. N equals 2, it's like the bird. You know, an n equals 1 bird has less energy than an n equals 2 bird. So the n equals 2 bird is going to be farther away from the nest. So if you're a predator, it's going to be easier to attack that than n equals 1. Does that make sense? No. And so the n equals 4 is going to be the furthest away. This is the furthest away with the greatest probability. Even though this is a little lower in energy than that, if you're going to attack an electron, you're going to take the one that's furthest from the nucleus, which is the n equals 4. Which isn't necessarily the highest energy electron. The highest energy is over here. It's just it's the furthest away. In a certain sense, the distances we have to look. I mean, what makes it? You know, electrons that are closer to the nucleus should be lower in energy. Electrons further from the nucleus should be farther, but it has to do with the shapes of these things. This whole shielding and penetration stuff we were talking about earlier, or I was talking about earlier, it's more involved. So in Chem 1A, you go into it in detail. In Chem 4, we're not. And so what we're going to do is we're going to get some practice identifying core and valence electrons as well. And so let's just take a look at this. If I look at hydrogen, how many core electrons does hydrogen have? None. It only has 1 electron. How many valence electrons does it have? 1. Hydrogen has 1 valence electron. Let's go to lithium. How many core electrons does lithium have? That would be the inner shell electrons. Well, maybe we should start with how many valence. How do we define valence? Valence would be the outermost electrons. And so when we look at lithium, lithium will have the first shell filled and then 1 electron in the second shell. And so in the second shell here, we have 1 electron. That means we have 1 valence electron and 2 core electrons. And so lithium has 1 valence electron, just like hydrogen. If we go to sodium, Sodium has the first shell, the second shell completely filled. And so the first shell and second shell are completely filled. That's like neon. So it has a neon core, and then the third shell has one electron. It was 3s1. And so how many valence electrons does sodium have? 1. Potassium? 1. Go to beryllium? 2. Magnesium? 2. Calcium? 2 valence electrons. Which one? For which one?
How did you figure out
Oh, how I figured out is, let's look at calcium. Let's draw the electron orbital energy level diagram for calcium. So number one, you should memorize this. You know, this is 1, 0, 0, 1s, followed by the 2, 0, 0, 2s. Then we have the 2 p's, 2, 1, negative 1, 2, 1, 0, 2, 1, 1, followed by the 3s. 3 p's. Followed by the 4s. What comes after the 4s? 3d. 3d is going to be higher in energy. And after the 3d, 4p. That's the fourth shell. So here we have the fourth shell. If we do calcium, we filled the first 3 shells. Filling the first 3 shells is up to argon. So we'll call this argon core. 1, 2. So the first shell is filled, second shell is filled, third shell is filled. This is stable, very stable. So these electrons aren't reacting. Where chemistry happens is in the outermost shell. That's where the oxidizers are going to come in, or that's where, if you're an oxidizer, that's where you're going to place the extra electrons that you need. And so this is 4s1, 4s2. The 3d are empty, the 4p are empty. And so the inner electrons here are called core electrons. So all these 18 electrons will be core. And the outermost electrons will be valence. So we just count them. How many valence electrons do we have? Well, how many total electrons in there, in the outer shell? 2. And so there's 2 electrons. Now, with the when we get to scandium, then things get a bit messy. Scandium, titanium, vanadium. You know, what's a very common charge for transition metals? +2. +2 is a very common charge for transition metals. Do you know why +2 is a very common charge for transition metals? Let's take a look. 1. If we go to scandium, scandium has like this. So technically, scandium has how many valence electrons? You would like to say 3. I'd like to say 3 because when I look at the outermost shell, I see 1, 2, 3 electrons. Look at that. But because of the way we define it, and it's a little bit tricky here, because of the way we define it, technically it only has 2. What are the 2 most outermost electrons? Well, they're the electrons in the highest n. And so when I look at scandium, 4s2, 3d1, I see there are 2 valence electrons, the 4s, n equals 4. Right? And this would be an inner. But that inner electron is not so stable. And so this inner electron can also be taken away because that's only one slice. You know, that's the last piece of cake there is. So somebody can easily come and take it. Right? There's no additional stability. associated with that. And so the most common charge for scandium is, and it's actually scandium's fixed charge. Do you know what the fixed charge on scandium is? Plus 3. And so what happens is oxidizer, when an oxidizer comes along, it's going to encounter which electrons first, the 4s or the 3d. You're a hungry oxidizer, you come along, which electrons do you encounter first? The 4s or the 3d? Well, maybe I should draw it. What does a 4s orbital look like? Forest orbital looks like a big sphere. 4s. What about a 3D? Well, what's bigger, 3 or 4? Like a 3s or 4s? What's bigger? 4s is bigger. 3s would be like this. This would be a 3s here. Actually, in terms of size, it goes like this. If a 3s is 9 times bigger than something, let's say 1s, okay. If we start off with 1s is like this. You know, a 3s is 9 times bigger than a 1s. Do you know what a 4s is? How many times bigger than? 16 times. A 4s is 16 times bigger than a 1s. So 4s's are quite huge. So this is not to scale. But what about a 3D? Well, 3Ds are going to be like the 3s's, you know, it's kind of cloverleaf type deal. So this would be like a 3D here. So if you're a hungry oxidizer looking for electrons, which electrons are you going to encounter first, the 4s or the 3D? The 4s. So when you're an oxidizer, you're going to pluck the 4s off first. So this is why normally we write the electron configuration like this: argon, 4s2, 3d1, because that's how we fill it. We fill it like this. This is the filling order. However, when we remove electrons, then we have the losing order. Losing order is an oxidizer comes along. The losing order is going to be like this: 3d1, 4s2. The 4s2 are furthest away, so if something's going to attack, it's going to attack the 4s2 first, and then the 3d1. So an oxidizer comes along here, it attacks the 4s2. If it takes both electrons, what charge do we end up with? We end up with +2. But if the oxidizer is hungry enough, then it can take the 3D as well. And so we end up with +2 and +3 with charge. So this is scandium. Let's go to the next one. Next one is titanium. Titanium, can you tell me what the charges are for titanium? Well, I'd say titanium +2 is 1 charge, right? And titanium +3 is possible, and titanium +4 is possible. And so here we can have titanium +2 if we take the 4s, and then +3 if we take one of the 3ds, and +4 take left. What's vanadium's charge? Well, vanadium is going to have 1 more electron. And so vanadium is going to be, well, which electrons are going to be lost first? The 4s. So vanadium +2 is potential. And then once we attack those, then what remains? The 3D. So vanadium +2, vanadium +3, vanadium +4, and vanadium +5 are potential charges for vanadium. Chromium. What are the potential charges for chromium? Potential charges for chromium would be chromium +2. We lose the first 2, the S. And then chromium +3. 3, which is very common charge. We just lose one of the D. Chromium plus 4, chromium plus 5, and finally chromium plus 6. Right? Chromium plus 6, or chromium 6 would be the maximum. Manganese. Manganese, what are the common charges for manganese? Manganese, you lose these. It would be manganese plus 2. Manganese plus 2 is very common. Then we lose this one. It would be manganese plus 3, plus 4, plus 5, plus 6, plus manganese plus 7. That's the max. The max for iron is quite high, you know. And so once we start losing a lot, then it becomes troublesome. Let's take a look at iron. What is iron? Iron is going to be 4s2, 3d, 6. What are the two most common charges for iron? Plus 2 and plus 3. So if we go iron plus 2, we lose those 4s. If we go iron plus 3, we lost one of these. Which one do you think we're going to lose? Yeah, the doubled one, this one. Because if we lose that one, then we're left with what? The half-fill D. And the half-fill D has that symmetry. Symmetry, we probably don't want to take another slice out of that. And so iron plus 2 and iron plus 3 are very common charges. When we look at the periodic table, cobalt and nickel are a bit more difficult. These are the max oxidation states here. So scandium's in group 3D, max ox is 3. Titanium's 4, vanadium's 5, chromium's 6, manganese is 7. Iron, cobalt, nickel, 8 would be the max, but this is rare. 2, 3 for iron. Cobalt would be 2 and 3, and nickel would be 2 and 3 common for nickel. Copper, however, copper is not. Look at this. This is group 1. This is group 1. So therefore, this is 1A. This is 1B. What's special about these? Well, in groups 1 and 2, in group 1, how many valence electrons do we have? We have 1. In group 2, we had 2. These are pseudo group 1 and pseudo group 2. And they're pseudo group 1 and pseudo group 2 because of this. What was the electron configuration for copper? It was the exception. It was 4s1, 3d, 10. And so a common charge for copper should be plus plus 1. Plus 1, we lose the 4s electron, so copper 1 is common. We lose the s electron, we don't want to mess with the d. The reason the d's, one of the electrons, copper plus 2 is very common. In fact, extremely common. And it doesn't make sense looking at the orbitals here because the d is a full cake. We don't want to lose a slice of the full cake, but there's a reason for losing a slice of a full cake. That reason is discussed in Chem 1B. I'm not going to talk about it here. But it makes sense that copper plus 1. Silver, however, is always plus 1. I told you to memorize 2 exceptions, chromium and copper, right? But also molybdenum, like chromium, shows the same, and silver, like copper, shows the same exception. And so silver is, we can use the periodic table to figure out the electron configuration for silver. Using the periodic table to figure out the electron configuration for silver, we start off with krypton. We filled the first shell, the second shell, the third shell, the fourth shell is filled. And so we start off with krypton, the filled fourth shell, and then move to the fifth shell. When we move to the fifth shell, we say 5s1, 5s2, 3d. No, actually that was 3. This is, if this is 3d, this is going to be 4d. So 5s1, 5s2, 4d1, 2, 3, 4, 5, 6, 7, 8, 9. So what I get is 5s2, 4d9. But 4d9 should tell you, what's special about 4d9? Well, d9 means it's just one electron short of being filled. And so this silver is an exception also. And the exception is it's going to be 5s, rather than 5s2, we're going to go 5s1, and then take that 5s electron, promote it to the d. So silver becomes this. Silver becomes krypton, 5s, 5s1, 4d10. How many valence electrons does silver have? 1. Because what we're going to do is we're going to rewrite this. This is equal to krypton, 4d10, 5s1. Now the thing is, this is a filled D subshell. Filled D subshell, do we want to mess with it? No, we really don't want to mess with it. And so what we're going to do is we're going to consider all these core, or inner shell. And so we say it has 1 valence electron. And so the 1 valence electron will be attacked. Sometimes we can attack the 4D, especially if it's not filled. If the 4D or the D sublevel is partially filled, it can be attacked. In this case, it's not. The only charge for silver is +1, and so we attack that last electron. Okay. Zinc is always +2. Cadmium is always +2. Can you see why zinc would always be +2? Zinc is always going to be +2 because take a look at the electron configuration for zinc. Zinc is always +2. Because his electron configuration is 4s2, 3d10. Argon, 4s2, 3d10. And so this has 2 valence. So if we take these 2 off, then what are we left with? We're left with 3d10. Do we want to mess with 3d10? Or not really. We'd like to leave that complete. We'd like to leave that whole. It's a filled sublevel. And so these 3d10, since that's a filled sublevel, we're going to call those core as well. So it's got the argon core plus this 3d10. We're going to consider core electrons. Sometimes the core electrons can react, like over here, like iron. You know, we'll have this, even though this is inner shell, this 3D, we're going to react it because we can, if it's partially filled. Sometimes the cores don't react. Now, what about gallium? How many valence electrons does gallium have? Does it have, some people will say it has, well, it has the argon, so it has the first shell, second shell, third shell filled, argon. And then the outermost shell is the fourth shell. The fourth shell is 4s2, 3d10, 4p1. Right? But do we consider that all of those orbitals in the fourth shell valence? No, we don't. In fact, when we look at the valence electrons are just going to be in the n equals 4 subshell. And so how many valence electrons does it have? 3. 2 from the S, 1 from the P. These 3d10, do we want to mess with those? No, we don't. And so this one only has 3 valence electrons. Well, what about aluminum? How many valence electrons does aluminum have? Well, we filled the first shell and the second shell, so that's neon. And then the outermost shell would be partially filled, 3s2, 3p1. How many valence electrons does neon have? 3. Boron has 3. So all these have 3 valence electrons. Germanium has how many valence electrons? 4, because these 3d10 we're not going to mess with. Silicon has 4, and carbon has 4 valence electrons. And so 3d10 here, arsenic has 5, selenium has, and bromine has 7. Now, when we get to the end here, which would be krypton, now we've completely filled the 4th shell. And so we filled the 1st shell, 2nd shell, 3rd shell, and now the 4th shell. And so valence electrons here, this is the filled shell. You can consider having, 8 valence electrons, or you could just call it filled. The 8's a special number, because how many valence electrons does krypton have? 8. How many valence electrons does argon have? 8. Neon? Helium? 2. And so these neon, argon, krypton have an octet of valence electrons. That octet is very special because it corresponds to filled outermost shell. Filled outermost shell, we don't want to take any slices out of that. And so krypton, argon, neon, helium is filled shell, but it only takes 2 to fill the first shell. All these are filled shell type configurations, which means they're stable and unreactive. So these used to be called inert gases because they were so inert, so unreactive. But it turns out if you have some very, very powerful oxidizers, you might be able to get them to react, except for helium and neon. You really don't, but argon and krypton can because they're much bigger. So these are called the Nobel gases now. The Nobel gases are unreactive. They only react under unusual circumstances, but they're unreactive. So they're inert. They're non-toxic. I mean, toxicity, people die from helium, but they die from, I think, not enough oxygen. Or there might be something with helium. People breathe in helium, those deep sea divers, they breathe in helium mixtures. All right, so this is quantum mechanics. Quantum mechanics tells us about the allowed energies and the orbitals are the allowed energies, and also what do we know about the position of the electron, the probability, of finding that electron. Probability because of what uncertainty principle? Who is that named after? Not Bohr. Bohr had the orbits. Schrodinger had the equation. Pauli had the orbital capacity. Hans had to fill one at a time. Heisenberg, because of the Heisenberg uncertainty principle, we have to look at it. Those are all really important. So these are the exceptions you have to know. You don't have to just know 2. There are more, like I said, silver, molybdenum. But you only have to memorize 2 of these. These 2 occur in the 3D section. Chlorine, they want the complete electron configuration. Now, chlorine, if you look at it, chlorine is just one slice away from filling that cake, whatever you want to call it. In order to fill the 3rd shell, it just needs 1 more electron. So rather than losing electrons like the other one, in the case of chlorine, it would much prefer to gain. So there's 2 ways we can get this filled shell. One way is we could lose, this is messed up. This is messed up because if we're going to do the electron configuration, well, my preference is not the electron configuration. My preference is the energy level diagram. So let's go with that. 1s, 2s, 2p, 3s, 3p. So we'll just do the first 3 shells. So the first shell is filled, second shell is filled. 3rd shell is almost filled. how many more electrons are required to fill the third shell? Just one. So if you're chlorine, you would much rather gain an electron. If you gain an electron, you'll fill that third shell and you'll be called chloride. But you could potentially lose electrons too. Chlorine can lose up to how many electrons could it lose? In other words, what's the oxidation state for chlorine range from? Yeah, -1 to +7. So chlorine's oxidation state ranges from -1, which is preferred. For sure it wants one more electron, to +7. And so -1 gains an electron, +7 loses 1, 2, 3, 4, 5, 6, 7, that entire shell. That would be +7. Is that easy to do? To get into +7? No, that's why chlorine in +7 is so extremely reactive. You gotta strip those electrons away. Could it go higher? Can it eat into the next shell? No. You know, because that would cost too much energy. So +8 means that we'd have to start attacking the second shell. It's filled. It's already stable. And so the theoretical basis for chemistry is quantum mechanics, because quantum mechanics gives us this. This is called an electronic structure. It tells us how the electrons are structured in the atom. So when we do this, the complete electron configuration would be 1s with 2 electrons, 2s subshell with 2 electrons, 2p subshell with how many? 2, 4, 6 electrons, 3s with 2 electrons, and 3p with 5 electrons, 3p5. If we use the abbreviation here, filling the first and second shell, that would be equivalent to neon. And so we could go 3s2, 3p5. So 1 electron short from filling that last shell. And so these electron configurations are wrong here. We made a mistake. Correct it. Oh, no, I guess it's not wrong. They fixed it, man. They just did it a different way than I do it. Do the electron configuration for cobalt. Cobalt, I'll tell you the easiest way to do these electron configurations is based off the periodic table. If you go to cobalt, here. I just read the electron configuration off the periodic table. That's the easiest for me. There's cobalt. So cobalt will be either, we just go back up to argon. Argon has 18 electrons, so we fill the first shell, second shell, third shell. So we've got argon, and then we go over here. It would be 1, 2, 3, 4, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7. Cobalt's not one of the exceptions, so it'd be argon, 4s2, 3d7. I don't know what they're doing with this stuff, because I just don't do it this way. 4s2, 3d7. I guess they're looking at its position here in the periodic table first. All right, valence electrons versus core electrons. So the valence electrons here, how many? Well, the highest n is 3. How many total? 5. Positive 5 valence electrons. The highest n. Total number of electrons in the highest n. So anyway, group 1 all have 1 valence. Group 2, 2 valence. Group 3, 3 valence. Group 4, 5, 6. Group 8, which would be the 8 valence electrons. Well, before we do that, let's try something. Oops, did I go overtime here? Or was it? Yeah, I went overtime. I forgot to take the break. Should we take a break now? Or just keep going? Take a break? All right, let's take a break.